So let's take a look at the non-polar covalent molecule. In the case of non-polar covalent molecules, the electron cloud, which is actually mobile, will actually be moving. At times, they may congregate in one area more than the other, giving rise to an instantaneous dipole, where this region, which has a congregation of electron, is delta minus, and the region which is short of the electron is delta plus. This is termed as an instantaneous dipole. And the instantaneous dipole could actually generate an induced dipole. And this is the interaction force or the type of intermolecular force between non-polar covalent molecules. Hence, we describe the intermolecular force between non-polar covalent molecules to be instantaneous dipole to induced dipole attraction forces, or induced dipole to induced dipole attraction forces. Let's take a look at now the factors that affects the strength of this instantaneous dipole to induced dipole attraction force. And we're going to call that in short IDID. IDID is dependent on two factors. The first factor is the total number of electrons. The larger the number of electrons a molecule has, the better able it is to polarize its molecule. So like in the case of chlorine. In the case of chlorine, you have two Cl atoms that are bonded together, and each Cl actually contains 17 electrons. So at an instant moment, there's a possibility that one of the electrons could go over. Vis-a-vis that, in the case of hydrogen, you'll find that hydrogen each only has one electron. So hence, we can say that the IDID between hydrogen molecules is significantly lower than the IDID in chlorine molecules. Evidently, if you look at the example of the boiling points of group 14 hydrides, you also follow the same trend as what we expect, as SNH4 has the largest number of electrons. The second factor to look at is the molecular area of the molecule. To look at this factor, we need to note that both molecules must share the same total number of electrons. So for example, we take a look at 2,2-dimethylpropane, which is this, and your pentane, which is this structure. Both pentane and 2,2-dimethylpropane are both isomers, which means they have the same number of electrons. However, in the case of pentane, the shape is more cylindrical. All right, vis-a-vis, the shape is more cylindrical, vis-a-vis that of 2,2-dimethylpropane, which is more spherical. When it's actually more spherical, electron cloud in the center no longer participate in the polarization of the molecule. Therefore, because of this, molecule with cylindrical shape or elongated shape would have a larger molecular area, better able to polarize the molecule, leading to a stronger IDID. And therefore, pentane has a higher boiling point than your 2,2-dimethylpropane.